How you doing, Dr. Ragab?
Good, good. How are you?
Dr. Ragab, I had a question about the project that's been bugging me, I guess. Are we supposed to include the weight on the stat? Are we supposed to include the dead load? Well, I guess the weight of the beams?
Okay, you do one of two things. You either calculate the own weight of the beams yourself and add it, and make then the self-weight multiplier by 0. Or you can calculate this
And leave it as
and put the self-weight multiplier by that.
okay.
Both are correct.
1 or negative 1?
It's, yeah.
Well, I guess negative 1
Yeah,
because it's
negative
going
one.
down.
Yeah.
Okay. I guess if we already calculated, I assume it might be easier to leave it as negative 1.
If you don't want to calculate it, you're not sure about your calculations, then just put this out. But
Okay.
section has to be entered correctly. The material is and mentions
It's the dimensions. Okay. All right. Thank you.
I've started, yeah. Just haven't finished. Started about a week ago.
Yes.
With the result on load combinations on loads stat software, what all diagrams and whatnot do you want? What do you need on a report from stat?
Okay. I need the of the independent force diagrams. The normal force diagram, shear force diagram, the bending moment diagram, and I need to have values on that figure. So you either plot them member by member so that you can the graph shows the value. But if you just plot the envelope of the, let's say, the bending moment diagram, it doesn't show the value. So you can plot this for the entire frame and then write the values by hand. So in this way, you just have one figure for the entire frame. But you're going to have to tag the value of the bending moment at the critical points, to start the end, the middle of each member, okay? And just label, put them on the row. That way you just need one figure for the bending moment like that, one figure for the shear force diagram, one figure for the normal force diagram. Yeah, it's the envelope of the normal force diagram and the shear force diagram. And you need that for each. If you're going to do it, you can do it for the entire frame, okay? But you just have to label, I need to see the values, okay, on the drawing. That's it. So you either label them by hand, you don't want to do this, then you're going to plot for each beam, okay? And you have to label your beam so that I can understand which beam is this, okay? Like it's the girder A, like for example, here the A has 3 spans, okay? Which part, which floor, okay? Which column, okay? Or you just plot one figure representing the entire frame, okay? And you label the dimensions. You understand what I'm saying?
You want us to print the analysis part of it?
No, no.
So those diagrams are really all we need to print.
The diagrams, your model, okay, your model frame without any diagrams, and maybe if you would like, just plot also the deflected shape, okay. That's something that you might plot, okay. But it's not a must. If you don't plot the deflected shape, there's no problem. And you plot anything if you would like to illustrate here, like let's say the life load cases, you can plot them from the STAD model, or you draw them by hand. Okay, so you can use the STAD model to illustrate your life load cases. For example, your wind load cases. Okay, you can use the STAD to, you input them in STAD and then you plot them from the STAD to show them in your report. Okay, or you draw them by hand, whatever you do. Okay.
And we're going to submit this on Blackboard, the file itself.
The file is going to be submitted on Blackboard. I'm going to send a link where you can, submit the stat file in Blackboard, while the report itself has to be printed and submitted by hand. Okay. Yes.
That by 11/4.
So originally it's supposed to be submitted on Thursday. How are you doing on the project? Will you be able to submit it on Thursday? Okay.
It'd be nice
we can push it to Monday. Would that be good? Okay.
That helps a lot.
Okay. So we're gonna push it. Look, the thing is, I want to be nice, okay? I want to push it further than Monday, but if I push it further than Monday, okay, that will affect, how you're doing in the other courses. You're gonna have finals. I don't want, to push it further than Monday, okay, and you work on your project and forget about the final. So I'm just gonna push it to Monday so that you can focus on your finals, okay? Yes.
Monday at 4, 11.
What time do you want?
We have 4. 4 works pretty good.
Okay, so Monday at 4. That's fine. No, not at 4. Monday at 3.
At what time?
3.
3.
Okay.
Is that both the stat and the portion that we're supposed to turn in class, or do you still want that?
Everything is on Monday at 3.
And turn it into your office.
Yes. Thank you. Okay, so now let's go ahead and continue our discussion of the influence lines. So last time we said you can find the shape of the influence line using something called Muller-Pressler principle. So what does Muller-Pressler principle says? If you want to find the shape of the influence line of any function, just displace your structure by a unit displacement in the direction of that function, okay? And the displaced shape represents the shape of the influence line, okay? So we took an example here. For example, this symbol beam. We want to find the influence line for AY, so the displaced shape. We just AY upwards. If AY is the vertical displacement at point A, so put the vertical displacement at point A. A unit vertical displacement at point A, and the displaced shape is the influence line. BY, just displace B upwards, the unit displacement at B here, and then this is the displaced shape. For the shear is two forces. This is the shear, okay? Shear force. So you just come here at C, you displace the beam like this, and that's the displaced shape that this, and the shape of the displaced shape is the shape of the influence line. For a moment, okay, you introduce a hinge here, and then you put a unit moment, okay, or a unit rotation, okay? Moment is two rotations like this, okay? And then it displays like this, and this is the shape of the influence line as well. And then we took this example, okay? I'm not going to go through it. We already solved it. And now let's see another example here, example 610. So in example 610, we have a set of beams and we want to draw the influence line for VB, the shear at point B, in each one of those, okay? So how to do this using Muller-Pressler principle? Just come at point B and displace it in the direction of the shear. Shear is just two forces. I'm just going to come over here, produce a break, and just put a unit shear displacement, okay? A shear displacement at point B. If this happens, you have two parts. The part that is right of point B and the part that is on the left of point B. How would those get displaced if you want to displace them? Okay? The thing is, the part on the right, okay, is supported by this support and this support. Okay, two supports here. Okay? So it's not going to be able to move or get displaced. While the other one is free, so it's going to move down like this. So that's the displaced shape. The left part is going to be able to move down, while the right part is not going to be able to move because there is two supports, so it's going to prevent it from moving up. Okay? So now that's the influence line for VB. This is how the influence line of VB looks like. The displaced shape. That height is 1K, or 1 the unit. Okay? That's the influence line of VB, according to Muller-Pressler principle. So what's over here? Just 0. What does this mean? If the load is moving on the right of point B, the shear at point B will always be 0. Okay? For any load that is on the right of point B, the shear at point B is 0. And then let's see the next beam. If we have cantilever beam like this, and this is point B, okay? We want to draw the influence line for the shear at B. How would we do this? Okay? Introduce a break here, okay? And then apply the unit shear displacement, okay? Again, the left part is attached to the support, okay? So it's tough to move it, while the right part will just get displaced like this, okay? If you put a unit shear displacement. So what's this? This is the displaced shape, and this is the same as the influence line for VB. It's positive, moved up, okay? It's 1K, and here it's 0. That means that if the load is on the left of point B, the shear at B is 0, okay? And then let's see another example. We have this beam. It's a compound beam. And we would like to draw the shear at point B here. Influence line for the shear at point B. How can I do this? Muller-Pressler principle says that you just introduce a unit displacement in the direction of the function that you're looking for. The function is shear at B, so I've just come here, introduce a unit shear. Okay? So now, if this happened, both are, there is just one support, so it can rotate, okay? Both parts, the part on the left and the part on the right. So when we draw the displaced shape, this is going to move up, okay? And then get connected to this part like this. Just it's going to rotate upward like this, right? This is the right part. If you push it up, it's going to rotate like this. The left part is going to, if you just push it down, okay, it's going to move down. And then here, there is a support, so it cannot move at the support, but it's going to go up here till the hinge and then go down like this. What is this? This is the displaced shape. If I just break the beam at B and just put a unit shear displacement, this is how the displaced shape is going to look like. The displaced shape represents the influence line of VB. The influence line of VB. So that's the influence line. How the influence line of VB looks like.
Okay? It's positive. Here it's negative, and here it's positive. Okay? And then let's see another example here.
So what are the values of that one? The values?
Okay, the values here, okay, is, you know, it's not straightforward to get, okay? The thing is that this total height has to be 1. Because you're putting a unit displacement. So the unit displacement is, part of it is here and part is here. So the total is 1, okay? And now, how much is this distance and how much is this distance? That depends on the length. So let's say this is A, this is B, and this is L. So this is going to be A divided by L, and this is going to be B divided by L. The total is 1, okay? And but it's not always, you're not gonna always be able to find the magnitude of the heights, okay? Because this is a quantitative method. Sometimes you're able to find the heights, and sometimes you're not. Okay, you're just able to find the shape. That's all. Okay.
Find the
Not the heights.
right. Would you find the left side the same way if you had to find a value?
Yeah, but by similarity you can find this height by similarity between those two triangles. Okay. So another example here, example 6.11. So in example 6.11, we're required to draw the influence line for MB for the shown beam, for the shown beams. So it's a set of beams. We're required to draw the influence line for the moment at point B for each one of them. The first beam that we have over here is a beam that looks like this. Let me give you a very important thing about MB. MB, when you have a moment, influence line for a moment, you break the beam, you release this moment, so you introduce an internal hinge, okay? And then you introduce your moment. The moment, it's in the positive direction, so actually it always makes the two segments intersecting at the point rotate close to each other, okay? So let's see what I mean by this. This is point B, okay? We want to draw the influence line for MB. So what I'm going to do is I'm going to break the beam here at B and introduce the moment, or the unit rotation, okay, the unit displacement. So I have to introduce this moment, okay, because otherwise the beam is not going to move, okay. I want to release, okay, or move it in the direction of the moment, okay. So I have to release it first, and then I'm going to apply this unit rotation. So now this unit rotation, 1 to here. If I'm rotating this like this, the two segments want to get closer to each other. This angle, 180, okay, is going to get smaller, okay? So, but the thing is, the left part over here, you have those two supports preventing it from rotating. So actually what will happen is it will just move like this, so that the angle gets smaller than 180, okay? You decrease the angle between the two segments. What's this? This is the deflected shape, okay? So the deflected shape represents the influence line for MB. It's negative over here, okay? B, if we have a beam that looks like this, a compound beam, okay, and we would like to find the influence line for MB. How would the influence line for MB look like, okay? Just produce a unit rotation at point B, okay, and put a unit, so introduce a unit rotation here at point B and release the rotation at point B to be able to allow the unit rotation at point B. So first I introduce the hinge to allow the rotation at point B, and then introduce a unit rotation. Now I'm pushing this like this, so both parts want to get closer to each other. So this is going to move up, okay? those are going to move like this. Okay? So it's going to move up, and then this is like this, and this is just one member. And then here at the hinge is going to get rotated like this. So this is the displaced shape. Okay? Any problem with imagining the displaced shapes? Does anyone have a problem here? Okay, so now this is the displaced shape. Simply the displaced shape represents the influence line of MB. So the influence line of MB looks like this. This is point B over here. This is the support and this is the hinge. And so it's negative and positive. Okay? Let's see here. Third one. Cantilever beam, and we want to draw the influence line for MB. How would we do this? We want to release the rotation at point B. So assume there is, like, we introduce this hinge to be able to introduce the unit rotation, and then apply unit rotation here at point B. Those two parts want to move like this, but actually this part is not going to be able to move up because it's, you know, fixed over here. Okay. So this is actually going to move like this. That's all. Okay? So what's this? This is the displaced shape, and it looks the same like the influence line of MB. This is negative. So here, always this angle, okay, gets smaller. This theta is less than 180. This your displacement, okay? Try to make this angle smaller. You're applying a positive moment to move them closer to each other. Okay? Now let's see a large example here, a long example on using the influence lines. So example 612. So in example 612, we're required to calculate the maximum positive moment at point D due to a concentrated force. Sorry, a concentrated live load of 4,000 pounds and a uniform live load of 300 pounds per foot and a dead load of 200 pounds per foot. We have a beam that looks like this. Point A, B, C, D is over here, and E is over here. The dimensions, this is 5 feet, 5 feet, 5 feet, 10 feet here. So let's see here, what are we required to do? There is a dead load applied on this beam of 200 pounds per foot. Where is the dead load applied? Everywhere. It's the dead load. The dead load, okay, is mainly comes from the weight of the structure. The weight of the structure is everywhere, okay? So it's 200 pounds per foot everywhere, okay? And then there is some life load. There are two life loads. There is a concentrated life load of 4,000 pounds and the uniform life load of 300 pounds per foot. Where are those applied? You don't know, okay? You need to find this yourself. Where would you apply those life loads? You need to apply them at the location that maximize the positive moment at point B, okay? At every location they are at, you know, the moment at point B is going to change. You want to put them so that MD is maximum, okay? That's what we want to do. How would we know where to put those life loads so that MD is maximum? How can you answer this question? Where would you put the life load so that MD is maximum? You have to draw the influence line for MD to answer this question, okay? So now, this is the first step. Draw the influence line for MD to be able to know the location where you're going to put your loads to maximize MD. So how would I draw the influence line for MD? Just, you know, release it, okay? So use the Muller-Breslau principle. Put a unit rotation at point D, okay? So how the displaced shape is going to look like? It's going to look something like this. Right? And then this represents the influence line for MD. It's negative here and it's positive here. Muller-Breslau didn't tell us how much is those heights, okay? We just know the shape, but how much are those heights we don't know, okay? I don't care about the heights, okay? It's very good that now we have the shape. Now, can you answer that question that we had earlier? What was the question? Where to put the life load so that MD is maximized? So first, let's answer we already answered another question. Where to put the dead load? The dead load is applied everywhere. So this is the dead load. This is the dead load, and it's how much? It's 200 pounds per foot. Okay? D equal 200 pounds per foot. And then we have the life load, the uniform life load. Where will you apply the uniform life load so that MD is maximized? MD positive is maximized. Where will you put it? Will you put any life load here? Putting any life load here will result in a negative moment at point B. How did I know this? Because this is what we have here, negative infinite for MD. So to have the maximum MD, you just put the life load over here. Okay? So we're going to have the life load here, added to the dead load. Okay? The dead load is something that you cannot avoid. Okay? And here you have a life load of 300 pounds per foot. That's for the uniform load. What about the concentrated life load? Where would you put it to maximize MD? MD positive. Where would you put that? At the maximum height, at the maximum positive height for the MD, in the influence line over here, which is at this point. So here I'm going to have the 4,000 pounds. this is the case, the case of loading, okay? That will give MD maximum. It's exactly like your project. You have different live load cases to maximize the moment at certain locations, okay? Here, this is one of the live load cases that maximize the moment at point D. If you would like to maximize the moment, let's say, somewhere over here, it would be a completely different load case, okay? So now we know that this is the case of loading, okay? The loading case to have MD maximum. Now we just want to find how much is MD maximum. How would you do this? Can you use the influence line to find MD maximum? If you knew those heights, you can definitely use the influence line, okay, to find MD, okay? Multiply the 4,000 pound by the coordinate of the influence line at that point, and then the magnitude of the uniform load by the area of the influence line. But you don't know those heights. So how would you calculate MD then? Just as you did earlier, okay? Find the moment at point D. Take a section at point D and find how much is MD. So to find the moment here, this is point D over here. I would like to find the moment at point D. So I just take a section and study the left or the right of the section. Which part would be easier to study? The left or the right? The right has less forces. So if you just take the section and try to find MD, okay, you will need to know how much is this reaction, okay? So here we need to know how much is this reaction, EY. So the first step we're gonna do now is finding the reactions. So find the reactions. I'm just going to be fast over here, so to find the reactions, I'm just going to draw the free body diagram for each part of the beams. I'm just going to split the beam at the hinge here. So here we have AY, and here we have BY, okay? And we have a load here, which is 200 times the length, which is 5 feet. So this is 1,000 pounds, okay? So that means that AY is 500 pounds, and BY is 500 pounds. Okay? Here, this gets inverted. So here we have 500 pounds, the inverse of the BY over here. And then we have, here we have the support, this is CY. And here we have EY. And here we have this uniform load, this part here, which is 300 times 5. So this is it? No, 200, sorry, that's the dead load. So 200 times 5, so that's 1,000 pounds. And then here, we have a dead load from C to E. We have the dead load and the life load. So the total intensity is 500 pounds. So 500 pounds times 15, okay? So here we have 500 pounds per foot times 15 feet. So that's 7,500 pounds. And we have the concentrated force of the 4,000 pounds. So now for this beam, for this section, if you take the summation of the moments at point E equal to 0, you will find the magnitude of CY, and it's going to be equal to 80 to 50 pounds. And then the summation of FY equal to 0, you're going to be able to find EY. So EY is 4750 pounds. All of this is to find EY so that I can take a section, okay, at point D. So take a section at point D. So now at point D, okay, we have here EY, which is 4750 pounds. At point D, this distance is 10 feet. What are the forces that we have? We have here 500 pounds times 10 feet. which is 5,000 pounds. Okay? Now at point D, I took a section here. We have MD, we have VD, and ND. Okay? I'm not interested in VD, I just want to find how much is MD. So to find MD, just take the summation of the moments at point D equal to 0, as you learned earlier. So you're going to have EY times 10 feet plus the 5,000 pounds times 5 feet equals to MD. So MD is going to be equal to 22,500 pound foot. Dividing by 1,000, this is 22.5 kips foot. This is MD. This is not any moment at point D. This is the maximum positive moment that can happen, okay, at point D. MD maximum that you were required to find. If you put the life load anywhere else, there is a moment at point D, but it's going to be less than this magnitude. Okay? You see, this is the powerful, how powerful is those influence lines. This is why we learned this topic about the influence line. The objective of using the influence line is to know where to put your load to maximize any function. Okay? Whether it's the moment at the point, a shear at the point, a certain reaction. Okay? You can only answer this question, where to put the load to maximize a function, only through the influence line. Nothing else can answer this type of question. Okay? Any question? Okay. So now I'm going to be a little bit fast. This part, we're not supposed to cover. It's not on the syllabus, okay? But I feel that, it's nice to cover it at this moment, okay? What's this? It's section 10, okay? This section covers the influence lines for indeterminate beams. So, how to draw an influence line, the influence line for an indeterminate beam? Nothing new, just use the Muller-Presslup principle, okay? So, draw or use the Muller-Presslup principle to draw the quantitative influence line. So this is, you're not going to be able to find any values. So let's see some examples. So here, example 10, okay, we have a beam that looks like this, okay? You're going to see a trick here, okay? A very important note that we're going to find here for indeterminate beams, okay? And here for this beam, as you see, it's an indeterminate, okay? The number of reactions are 4, okay? And you only have 3 equations of equilibrium, so it's an indeterminate beam. And we're required to draw the influence line for AY, okay? So how would I draw the influence line for AY? Displace it, move this up, okay? But it's not allowed, you just release the vertical displacement, you just push it up, okay? But it's not allowed to rotate, so the rotation here should be 0, okay? So here, the rotation should be 0, okay? Because you didn't release the rotation, you just released the vertical displacement, okay? So you push it up, and then it wants still to be horizontally because you didn't release the rotation. But it needs to move down to the support over here. So the displaced shape will look like this. What's this? It's a curve. So this is a very, very important remark that you should note here. For determinate beams, the influence lines are straight lines, okay? While the influence line for indeterminate beams are always curves, because there is a level of support, okay? A higher level of support that will not allow the displaced shape to move freely. It's going to always be curves, okay? That's an indeterminate beam is a beam with more supports, right, than actually needed. That's why it's going to always be curves here. So this is one, and this displaced shape represents the influence line of AY. It's positive like this, but it's a curve. So this is an important remark, okay? Influence lines for determinate beams are always lines, straight lines, while influence lines for indeterminate beams or structures are always curves. Okay, let's see another example here. A beam that looks like this. Okay, A, B, C, D. Let's say we would like to draw the influence line for VD. The shear at point D. So drawing the shear at point D here, what would we do? We release the displacement here, and we apply this shear. So this is going to go up and down. And now for the the right part, you have two supports, okay? So actually it's going to go like this. Here the displacement is 0, and here it's 0. So as you see, it's a curve, and a curve here, okay? This is how you displace it. Break it and you displace it like this. So now that's the influence line of VD. Okay? It's negative here, it's positive here, it's negative here. Let's see another example. Example 10-12. Okay? It's the same beam, and A, B, C, and now we're required to draw the influence line for MD. How can we do this? Introduce, okay, a hinge here. So we're going to introduce a hinge here, okay, and then put the unit rotation. So putting a unit rotation, this is going to move like this. That's the displaced shape, okay? So now this is the influence line for MD. It's negative here, and it's positive here, okay? Let's see another example here, okay? That is related to the project, okay? It's not in the textbook, okay? But let's see here, this example, okay? This example is for the project. Because you remember for the project, I told you there are 4 live load cases that you have to do, right? Putting the live load cases at, one panel and leave one panel unloaded, right? And then 2 panels and leave 1 panel unloaded. Why is this? We're going to see why is this now, okay? We're going to learn this now. So let's say here you have beam that looks like this, okay? Let's assume even, okay. This is A, B, C, D, and then the mid sections here are E, F, and G. You would like to maximize the moment at point E, maximize the moment at point B, maximize the moment at point F, C, G, okay? How would you maximize the moments at those locations? Where would you put the load to maximize the moment at those locations? You have to draw the influence line for each one of those, okay? So let's start drawing the influence line for each one of those. Now, the influence line for ME. How would I draw the influence line for ME? Just introduce a unit rotation at point E. And this is the displaced shape. Okay? So it's positive here, negative here, and positive here. So to maximize the moment at point E, okay, you need to have the live load on this panel, panel AB. Don't put any live load on panel BC because it's going to minimize it, not maximize it. And then put the live load here on CD. So you have it on one panel, leave one panel unloaded, and then one panel. Okay? Let's see how to maximize the moment at point E, point B, sorry. Just introduce the unit rotation at point B. So here, at point B, there is a support, so it doesn't allow the point to move up, okay? But we can rotate here. This is point C here, B, C. So it's negative here, and positive here. So actually, the moment at point B, if you want to maximize it being a positive load, you're just going to put the live load here. If you want to maximize the negative moment, you're going to put the live load here and here. So 2 panels. Okay? Just put the live load on those 2 adjacent panels and leave this panel unloaded. This will maximize the negative moment at point B. And then the moment at point F, the influence line for MF. Just introduce a unit rotation here at point F. This is point F, this is C, this is B. So it's negative here, positive here, negative here. So to maximize MF, I'm just going to put the live loads on the, mid span, BC. Okay? And then to maximize MC, just draw the influence line for MC. This is point B, this is point C. The influence line for MC. How would I draw the influence line for MC? Just introduce a unit rotation at point C. Point C has a support, so it's not going to be able to move up or down, but it's going to be able to rotate like this. It's positive here, negative here. So to maximize the negative moment at point C, I just have to put the load on those 2 adjacent panels, BC and CD. Okay? And then MG. The influence line for MG. Just introduce a unit rotation, point G, and draw the displaced shape. It's positive here, negative here, and positive here. So from those influence lines, you will find that, those are the load combinations that you had for your live load in the project. Okay? 4 live load cases. Live load here and here. Live load here and here. Live load here. Live load here and here. live load here, and here this is a repetition of this one. So 1, 2, 3, 4 live load cases. This one is exactly the same like this, right? The shape of the input sign is not the same, but it will lead you to put the live load here and here. So it's not a new live load case. Okay? Now you understand why I told you to put those, or to test those 4 live load cases. Okay? Any question? Okay, great. So now we're going to start a new topic, okay? Which is calculating the deflection in beams, okay? So deflection in beam. So let's say we have a beam that looks like this. Any beam, okay? And there is some loads applied on this beam. Those loads will give you some internal forces, okay? And we learned how to calculate those internal forces. It will give you some reactions, and we learned how to calculate those reactions. But it will also cause the beam to deflect. So the beam is not going to remain unpacked. It's actually going to have some deflection due to those applied loads. There is a huge difference between a rigid body displacement where you don't have enough supports to prevent your structure from moving, and from deflection, okay? Deflection is completely different. Deflection, your structure remain in the same position, but there is small deformation, okay? Due to the applied forces, okay? But your structure didn't move as a whole, okay? Your structure would move entirely if you have insufficient supports, okay? But here you have sufficient supports. Your structure is not going to move, but there is some deflection, okay? So now, our topic now is we want to calculate that deflection. As you see here, the deflection is not the same, okay? Every point has a different value of the deflection, vertical deflection. For example, here at the support, how much is the deflection? It's 0. But as you go inside the beam, the deflection changes, okay? So as you see, if this is the distance x, okay, the deflection, if we name it v small, okay, it's variable. So here, the deflection at any point, we're going to name it v small, okay, is variable with and is a function of the distance x. It's not constant. So we need to know how would we calculate this v. What caused this deflection? It's the applied forces. So you apply a force. You have some internal forces. Those internal forces will give you some deflection. Okay, will be the cause of that deflection. Okay. So what's the relation between the loads or the internal forces and the deflection? Okay, I'm not going to prove this. You're going to have it proved in the mechanics of material class. Okay, and it's a prerequisite of this course. So in the mechanics of material class, you have this formula: d2v by dx squared is equal to m divided by ei. This is the relationship that gives you the deflection. V is the deflection. Okay, it's v small, not the shear. The shear is v capital. Okay, so it's d squared v by dx squared is equal to m. Okay, the moment divided by ei. M is the internal moment. Okay, the bending moment. Okay, so what's ei? E is the modulus of elasticity of the material that the beam is made of. Okay, so as you have a stronger beam, or you use, let's say, steel versus wood, the deflection is going to be much less in steel versus wood. Although the load is the same, maybe the beam looks the same, but the different material, okay, will make the deflection different, okay? I is the moment of inertia. What's the moment of inertia? You learn this in static. For example, if you have a rectangular beam like this, with a width b and a height h, okay? So I is a property of that section, it's bh cubed divided by 12, okay? So I represent how stiff is your beam, okay? Regarding the deflection. As it becomes stiffer, the deflection gets less, okay? So this equation here, d2v by dx squared equal m divided by ei, it will give us the deflection, okay? What about the rotation? If I see here, if you see the beam here, there is an angle of rotation at each point, and this angle changes as well from one point to another, okay? This is a deformation that happens in the beam as well, okay? The beam is having some angle of rotation, okay, when you apply some load. How would you calculate this theta? Is it a different relationship? No. Theta is actually dv by dx, okay? So once you know the deflection, you can just differentiate it, find the angle theta. So this is the rotation, or the angle of rotation in the beam. So now, how can we find the deflection at any point due to a given load, or the rotation at any point due to a given load? We just wrote that this is the equation that we have. How we're going to use this equation to find v, or theta, okay? So simply here, we have a method called double integration method. How to use the double integration method? The double integration method, we just make use of this relationship, d2v by dx squared is m divided by ei. If I want to find v, you just integrate this equation twice to find v, okay? So first I need to know m, okay? So the first step here is to find m. So find the equation of the moment m, and then integrate m divided by ei once. Once you integrate it, okay, you integrate it once, you get what? You get dv by dx, which is theta, right? So this is just the integration of m divided by ei dx. And then you integrate again, to get v. That's how simple the method is. You start from this equation, you integrate it once, you get theta, you integrate it once again, you get v. A double integration method, okay? So let's see some examples here on how we're going to apply this. So example A3. We have a beam that looks like this. It's a simple beam with a length L that is equal to 10 meters, and there is a uniform load applied on top of this beam. The uniform load is W, and the intensity is 4 kilonewtons per meter. Okay? Here we're required to find the maximum deflection for the shown beam. How much is the maximum deflection here? Okay? So the thing is, if this is a distance x, the deflection shear, the deflection v in the vertical direction the beam under this load is going to deflect this way. As you see, the deflection is not constant. It changes from one point to another. Okay? If we call this point A, how much is the deflection at point A, and how much is the deflection at point B? 0. There is no deflection. Okay? The deflection is inside the beam. Okay? The maximum deflection, if it's obvious that the maximum deflection is right in the middle. Okay? But what's the equation for the deflection here? That's what we want to find. Okay? So how would we do this? We're going to use the double integration method. What does the double integration method say? It says that d2v by dx squared is equal to m divided by ei. M is the moment at any point. Is the moment constant? In this beam, is the moment constant? Is it just one value? No, m changes as a function of the distance x as well. Okay? So I need to find the equation for m. Okay? What's the equation for m? So this is the first step. Find the equation for m. M is the bending moment at any point. Okay? So now, to find the equation for the moment at m, okay, how much are the reactions here? This load is going to be WL. So this reaction is going to be WL divided by 2. This reaction is going to be WL divided by 2. Right? So now, taking a section, do you remember how you used to write the equation? Okay? You were tested for this on the first test. Okay? So find the equation for m. So to find this, take a section at a distance x. Okay? So I'm just going to take a section here at a distance x and find how much is the moment here. This is WL divided by 2. We have some uniform load here, W, and this distance is x. We took a section here, so we have m and we have v as well, right? But I just care about m. How much is m? So if we have this load, W, just finding its equivalent, it's going to be Wx, right? And now m is just WL divided by 2 times the distance x minus Wx times its distance, which is x divided by 2. So the moment at any point is WLx divided by 2 minus Wx squared divided by 2. What did I find over here? Just the equation that gives me the moment at any point at the distance x. Okay? Why do I need this? To plug it in this equation and then integrate it twice. Okay? So now, what does this equation say? It says d2v by dx squared is m, and don't forget that this is divided by ei. How much is EI? It's not given, but it's constant. The section of the beam, it's the same material, and the section doesn't change from one point to another. So I have here 1 divided by EI, and then the equation for the moment, it's WLx divided by 2 minus Wx squared divided by 2. Okay? What would I do next? So here, let's see. Just 3 simple steps. Find the equation for the moment. We just did this. What's the second step? Integrate the equation that you have here to find theta. Okay? So now, by integration, theta is equal to dv by dx is equal to the integration of m divided by ei dx. So now the integration here, 1 over ei has nothing to do with dx, so it's constant. So I'm going to move it outside the integral. So WLx divided by 2 minus Wx squared divided by 2 dx. So theta, or dv by dx, is equal to 1 divided by ei. Now let's do the integration. WLx divided by 2, when you integrate it, how much is it? divided by 4. And then you integrate the second term. How much is the integration of the second term? Wx cubed divided by 6. Okay?
Plus a constant. Plus a constant.
Plus a constant. Okay? So plus some constant here. Okay? I'm going to name it C1. Okay? So don't forget the constant. Okay? This is the equation that gives you the rotation at any point in the beam. Okay? If you want to find the rotation, the angle of rotation, theta, at any point in the beam, just plug x, the location of the point, you're going to get theta at that point. But you don't know how much is C1. Okay? So we're going to see how we're going to find C1. But now let's go through the third step. What's the third step? You integrate again. You're integrating theta now, so you're going to have V. You're integrating dV by dx, you get V. So now I'm going to integrate this, okay? It's equal to the integration 1 over EI WLX squared divided by 4 minus WX cubed divided by 6 plus C1 dx. How to perform this integral? What's the integration of the first term? You add 1 to the power here and then divide by the new power, so that's 12. Add 1 to the power and divide by the new power, so that's 24. C1, so it's going to be C1x. Anything else?
Plus
Another constant, C2. So this is the equation for the deflection. This equation gives you the deflection at each and every point on the beam. Just plug x, you're going to find the deflection at that point. But you have a problem here, because this equation has two constants that you don't know how much are they, C1 and C2. So how can I find C1 and C2? To find some constants, you need some information to guide you to find those constants. What information do you have? I asked you this and you answered it correctly before, but you just forgot that you know this now.
No,
W.
W.
You know W, okay, but this is not gonna give you C1 and C2.
L.
You know L, but again, it's not gonna help you, okay? And instead of just having W here, you're just gonna put 4. Instead of having L, you're just gonna put 10.
Reactions.
The equation for the deflection has nothing to do with the reactions. Right? You know the magnitude of the deflection at 2 points, and A and B. You know that the deflection at point A is equal to 0. So if you plug x equal to 0, you know that the deflection has to be equal to 0. And you know that the deflection at point B, where is point B? At x equal to L. Okay? You know that the deflection is equal to 0 as well. Right? So I'm going to use those two boundary conditions, okay, to find how much is C1 and C2. So use the boundary conditions BC, okay, to find C1 and C2. What are the boundary conditions that I know here? I know that at x equal to 0, okay, V is equal to 0. What's this? This is point A. So let's plug this. In the equation that we had, just put x equal to 0 and V equal to 0. V is 0 when x, so whenever I find x, I'll just put it 0. So you're just going to have C2, right? Just put x equal to 0, it's going to cancel. X equal to 0 is going to cancel. X equal to 0 is going to cancel. We're just going to have C2. So here, how much C2 must be? C2 must be 0. Otherwise, the deflection at point A is not going to be 0, right? This is the only value for C2 that satisfies my boundary condition. So now I know how much is C2, okay? So therefore now V is equal to 1 divided by EI WLX cubed divided by 12 minus WX power 4 divided by 24 plus C1X. There is no C2. Okay? Now, what's the other boundary condition? At X equal to L, V is 0 as well. What's this? This is point B. We have a support that prevents the deflection. Okay? So there is no deflection. So let's put the shear equal to 0, okay? And put X equal to L. So here we're going to have W. I'm just going to remove X and put L. So we're going to have L power 4 divided by 12 minus W L power 4 divided by 24 plus C1 L. Solve for C1. Just add those two terms and move them to the left-hand side of the equation and then divide by L to find C1. So you're going to find that C1 is equal to negative W L cubed divided by 24. Okay? So now I know V is equal to 1 divided by EI. I'm just going to put this value of C1 in the equation. WLX cubed divided by 12 minus WX power 4 divided by 24 plus C1, which is negative WL cubed divided by 24 multiplied by X. This is the equation for the deflection at any point. The equation for the deflection at any point at a distance x. Now we would like to find V maximum, the maximum deflection. Where is the maximum deflection? By visual inspection, it's right in the middle of the beam. If you don't know how to, you're not, satisfied with this visual inspection, how would you find V maximum? V maximum happens at the point where dV by dx is equal to 0. So you just differentiate this, equate it by 0, and find the location. You will find that it's at x equal to L divided by 2, just the middle of the beam. Okay? So now, to find V maximum, just plug. Every time you find x, just remove it and put L over 2. So 1 over EI, WL, L over 2 cubed divided by 12 minus W, L over 2 power 4 divided by 24 minus W, L cubed divided by 24, L divided by 2, and V max is going to be negative 5 WL power 4 divided by 384 EI. What does the negative sign mean? That the beam is deflecting downwards. That's something that you expect. V here is not, the points are not moving up, okay? They are moving down, okay? So it's negative. The maximum deflection here is negative 5 WL power 4 divided by 384 EI. On the cover of your book, okay, the inside cover of your book, you will find many values for the deflection calculated and written over there that you can use right away. Okay? So this is the magnitude of the maximum deflection for a uniform, for a single beam with a uniform load applied on it. Okay? So now just apply, in the problem we had W equal to 4 kilonewtons per meter and L was equal to 10 meters. Just put those in the equation. So V maximum is negative 5 times 4 kilonewtons per meter times L, which is 10 meters to the power 4, divided by 384 EI. So it's negative 521 divided by EI. And the units is in meter. Okay? I don't know how much is EI, so I'm just going to leave it as a constant. Okay? Any question? Okay, let's see another example here. So example 8.4. In example 8.4, we have a cantilever beam of a length L, and there is a moment here, M naught, okay, applied on it. We're required to find the elastic curve equation. What's this? Elastic curve equation. The beam is going to deflect, okay, somewhere like this, okay, due to the applied moment, okay. The equation for the deflection is the elastic curve equation, okay. So the elastic curve equation is just the equation for the deflection, V of x. This is what you're required to find, okay. So this is what the elastic curve equation means, V of x. So how to do this? The double integration method tells you 3 steps. Write the equation for the moment, divided by EI, integrated once you get theta, integrated twice you get the deflection, okay? So the moment here, what's the moment at any point, okay? Let's take here a section at the distance x, and x, I'm measuring it from the right point of the beam. So that's point A, that's point B. So now taking a section here, this distance is x. If there is a moment here, M naught, how much is the bending moment here? There is nothing but this M naught. The summation of the moments, okay, should be equal to 0. So if you have M naught here, how much is this moment? It has to be M naught as well, but just opposite in direction, right? Is this a function of the distance x? No. Wherever your point is, the moment is constant, okay? So M is equal to M naught, it's constant, okay? It's not changing. The moment at any point is equal to M naught, okay? So now, d2v by dx squared is equal to M divided by EI. M is a constant value, M naught, divided by EI. And then, what should I do? Integrate this equation once. So theta is dv by dx. So integrate M divided by EI dx. So I'm integrating M naught divided by EI dx. What's the integration of M naught? M naught is a constant. EI is a constant. So what's the integration of a constant multiplied by dx? X plus some constant C1. Okay? So that's the equation for theta. Okay? Now, integrating again. Okay? V is equal to the integration of theta dx. So now I'm just integrating this M naught x divided by EI plus C1 dx. So doing this integration, the deflection at any point is M naught x squared divided by 2 EI plus C1 x plus C2. That's the deflection at each and every point. Okay? Is this is the equation that we're looking for? Yes, but with 1 or 2 problems. We don't know how much is C1 and C2. How would we find C1 and C2? Use the boundary conditions to find C1 and C2. How many constants you need to find here? 2, C1 and C2. So how many boundary conditions you need to know? 2. You need 2 pieces of information, okay, to find C1 and C2. Okay? Do you know 2 information to find C1 and C2? Yes. Although we don't have 2 supports, okay? We only have 1 support at point A, so we know that the deflection at point A is equal to 0. So this is one of the information that I'm looking for. The deflection at point A is equal to 0. Okay? The second information is the support at point A is a fixed support. So it's not only preventing the point from deflecting, it's also preventing the point from rotating. Okay? So theta here, theta is equal to 0, and the deflection is equal to 0. So those are the two conditions, boundary conditions that we're going to use. So let's put the first condition here. Theta is equal to 0 at point A, where x is equal to 0. So I'm just, where's the equation for theta? This is the equation for theta. So just put theta equal to 0 and put x equal to 0 plus C1. So C1 is equal to 0. So that's the first constant. And then now, therefore, V, the deflection, is m node x squared divided by 2ei plus C1, which is 0. So it's just C2. And now let's use the second boundary condition. V is equal to 0 at point A, which is at x equal to 0. So just put 0 and put x equal to 0. So we have 0 plus C2. So actually C2 must be 0 as well. So therefore, the elastic line, or the elastic curve equation, is just V is equal to m node x squared divided by 2ei. This is what we're looking for. Any question? So here this is because it is fixed. Any questions? Okay, great. So see you next time on Thursday, the last lecture.
Thanks, bro.
You looking at as far as on the final exam, have we picked a date, or are we just going by the schedule the university uses? Third, I think.
Thursday, 12:30.
Right. Thank you.
Good. So I already did give you the invitation to the Taste of Africa.
Oh, okay, yeah, I received it.
Okay.
So it's on Saturday at 6, right?
Yeah. Saturday at 6.
Okay.
Hope to see you there, sir.
Yeah,
Oh,
I
and
might
I'm
bring
gonna-
my two sons.
Oh, I didn't know you had kids. Okay,
Two
that's
sons.
cool. Okay, how old are they?
One is 4 years old. The other one is like 9.5.
9.5? Okay.
Yeah.
That's cool, because I know Dr.